The objective of this lecture is to provide the third part of the study of the orbit in space. This lecture focuses on determining position and velocity from the orbital elements. This lecture is divided into the following parts. First, the overall structure required to compute position and inertial velocity from orbital elements is presented. Next, a derivation is given that determines the position and inertial velocity expressed in Earth-centered inertial coordinates given the orbital elements and the gravitational parameter. Now, a key aspect of this derivation is that 313 Euler angles are used for the angles omega I and little omega, where omega is equal to the longitude of the ascending node I is equal to the orbital inclination and little omega is the argument of the periapsis. Now, these three angles are particularly important because we have to use them in a 313 Euler angle sequence as part of this derivation where we transform from orbital elements to position and inertial velocity expressed in the Earth-centered inertial Cartesian coordinates. So let's get started with the rest of this lecture. So recall the classical orbital elements. And these quantities were A, which is the semi-major axis, E, which is the eccentricity, big omega, which is the longitude of the ascending node, I, which is the orbital inclination, omega, which is the argument of the periapsis, and finally nu, which is the true anomaly. And also, let mu be the gravitational parameter. Now, given this information, the objective is to determine the position and inertial velocity of a spacecraft given the 6 classical orbital elements and the gravitational parameter. So in this lecture, we're going to actually start with these quantities that I have on this page here, and we're going to work our way through the calculations to be able to figure out the position and the inertial velocity expressed in Earth-centered inertial coordinates. So in order to get started determining the position and velocity from the classical orbital elements, we're going to start with the perifocal coordinates. So recall the perifocal basis. P is equal to px, py, pz. Now this basis, when viewed in the orbit plane, looked as follows. So here's the ellipse. Here's the focus, which is at point O. Here's the periapsis at point P. The vector from O to P is the eccentricity. And the unit vector in the direction of the eccentricity was denoted px. Now pz was the direction out of the page, which also happened to be in the same direction as the specific angular momentum. And py is the vector that completes the right-handed system such that px, pyz, py, pz is in the order 1, 2, 3. Now, the position of the spacecraft relative to the focus was denoted r. And so the spacecraft is at the end of this vector, r. And the angle between r and e is nu. So that's the starting point. The reason that's the starting point is because let's suppose that it is possible to determine R and VI expressed in the perifocal basis. Given the orbital elements A, E, omega, I, little omega, and nu, and the gravitational parameter mu. In other words, if I'm given the 6 orbital elements in mu, if it's possible to determine R and V expressed in the perifocal basis, then that implies that we can obtain R expressed in P and VI expressed in P. Now let I equal Ix, Iy, Iz, which is equal to the Earth-centered inertial basis. So that's the basis that we've developed, which is the reference inertial basis based on the common coordinate systems that we had developed earlier, and the orbit is as such. So I'm not going to get into the details of what's in the diagram, but that's the original picture. And if I use that terminology for the Earth-centered inertial basis, suppose that the direction cosine matrix from P to I is known. And we'll say let CP to I be this direction cosine matrix. So now suppose that that matrix is known. So then what happens is as follows. So assuming that CP to I is known, the quantities are expressed in P and VI expressed in P can be transformed to the basis I, which is of course equal to Ix, Iy, Iz, as, well, we have R expressed in I is equal to the transformation from P to I times R expressed in P, and VI expressed in I is equal to the transformation from P to I times VI expressed in P. So if we know this transformation from CP to I, and we also have the position and the inertial velocity expressed in the perifocal basis P, then we have everything we need in order to be able to get the position and velocity expressed in the ECI basis I. And that's how this derivation is going to work. We're going to figure out the position and the velocity of the spacecraft in terms of the perifocal basis, and then we're also going to determine the transformation from P to I. And then we're going to put these two things together to get the position and velocity in the ECI basis. So the first part is going to be determining CP to I. Now, this transformation from P to I is actually determined using the three Euler angles, omega I and little omega. So recall that omega I and little omega form a 3-1-3 Euler angle sequence. And each of these rotations is a successive rotation about a successive axis, which is why it's called a successive rotation. And we're going to use these three rotations to determine CP to I. And we're going to do that now. So rotation 1 is about the 3-axis by the angle omega. So now let's look at this first rotation. We're starting here with the basis ix, iy, iz. So here's ix, here's iy, and here's iz. Now, we perform this rotation to construct a new basis, which is going to be called n sub x, n sub y, and then n sub z is the same as iz. And the angle of the rotation is omega. It's big omega. So from this diagram, we actually see that n sub x has to equal cosine omega times ix plus the sine of omega times iy. We see that ny has to equal minus the sine of omega times ix plus the cosine of omega times iy, and nz equals iz. Now from this relationship, we actually get that the transformation from n to I is equal to, we get the following matrix. We get cosine of omega, sine of omega, 0, minus the sine of omega, cosine of omega, 0, 0, 0, 1, where we're going to denote n is equal to nx, ny, and z. So now I have the transformation from n to I. So now we're going to go on to the second rotation. So rotation 2 is about the new one axis by the angle I. So given that I'm rotating about the one axis, I'm going to start with the basis nx, ny, nz, but now I'm rotating about nx. And that results in a new basis, which is qy and qz, with nx staying the same and resulting in qx. And the rotation is by the angle I. Now I can write out what these basis vectors look like relative to one another. So qx is equal to nx. qy is equal to cosine of I times ny plus the sine of I times nz, and then qz is equal to minus the sine of I times ny plus the cosine of I times nz, from which we actually obtain the following transformation. The transformation now is from q to n, and it's equal to, well, the first column is 1, 0, 0. The second column is 0 cosine of I, sine of I. And the third column is 0 minus the sine of I, cosine of I. And in this case, the basis q is equal to qx, qy, qz. That takes care of the second rotation. So then we move on to the third rotation. And it's about the new 3-axis by the angle little omega. And this geometry looks a lot like the first rotation, where in this case we're starting with the basis qx, qy, qz, and we're doing the rotation about qz, because that's the 3 direction. And that results in the perifocal basis. So this end result of this rotation here is in fact the perifocal basis. And this angle is little omega. So now we can write out the relationships between P and Q. So we've got Px is equal to cosine of omega times Qx plus the sine of omega times Qy. And we have Py is equal to minus the sine of omega times Qx plus the cosine of omega times Qy. And then we have Pz is equal to Qz. So as a result, we get the transformation from P to Q is equal to cosine of omega, sine of omega, 0. And we get minus the sine of omega, cosine of omega, and 0, and then 0, 0, 1, with, again, P equaling Px, Py, Pz, which is the perifocal basis. So now we have 3 transformations that we can write down. So these 3 transformations are as follows. Which are, we have Cn to I, which is equal to cosine of omega, sine of omega 0, minus the sine of omega, cosine of omega 0, 0, 0, 1. That's the first one. The second one is the transformation from Q to N, which is equal to 1, 0, 0, 0, cosine of I, sine of I, and then 0 minus the sine of I and cosine of I. And finally, we have the transformation from P to Q, which is equal to cosine of little omega, sine of little omega, 0, minus the sine of little omega, cosine of little omega, 0, 0, 0, 1. Now what I can do with that is as follows, is if I have a vector b, so we're going to say let b be an arbitrary vector. Then what I can do is as follows. So suppose that b is expressed in the basis p. So in other words, we are given b expressed in p. So then, if I want b expressed in q, that's equal to the transformation from p to q times b expressed in p. Similarly, if I want b expressed in n, that's equal to the transformation from q to n times b expressed in q. And then finally, b expressed in I is equal to the transformation from n to I times b expressed in n. Now, if I just go through and substitute, what that winds up giving me is b expressed in I is equal to the transformation from n to I times b expressed in n. But b expressed in n is the transformation from q to n times b expressed in q. But b expressed in q is the transformation from p to q times b expressed in p. And we also know that b expressed in I has to equal the transformation from p to I times b expressed in p. So that implies that the transformation from p to I has to equal the transformation from n to I times the transformation from q to n times the transformation from p to q. So we've just determined the transformation from p to I purely in terms of orbital elements. So this is now given completely in terms of orbital elements. And in fact, it's only given in terms of 3 of the orbital elements because we don't need any of the other 3. We only need those 3 Euler angles to be able to do it. So this is purely a function of the angle big omega, little I, and little omega. And that gives us that transformation. So now the next part is we need to figure out how to express the position and the velocity in terms of the perifocal basis. Because once we have that, we're done with this entire process. So this next part is going to be a method for determining R in P and VI in P. So here's how this works. Again, let's go back to the picture of the ellipse for a minute. So here's the focus. Here's the periapsis. This direction is px. This direction is py. And the spacecraft position is given, and so is the true anomaly. So we know that R is equal to R UR, where this direction along R is UR, and I'm going to complete this basis. This direction is U sub nu, and then the direction out of the page is UZ. Now this basis is fixed in a frame I'm going to call U. So from this, we know that the inertial velocity is equal to, well, it's the rate of change of the position in the inertial frame, which is equal to the rate of change of the position in U plus the angular velocity of U and I crossed with R. But the angular velocity of U and I is just nu dot times UZ. So this gives R dot UR plus nu dot UZ crossed with RUR, which is equal to R dot UR plus R nu dot U nu. So now we have a starting point for being able to figure out how to proceed further. So therefore, R expressed in U is equal to R0, 0, and VI expressed in U is equal to R dot, R nu dot, and 0. Now we're going to use the properties of the orbit equation to be able to simplify this expression for the inertial velocity expressed in the basis U. So we know from the orbit equation that the radius is equal to P over 1 plus E cosine of nu. So from that, we can get that R dot is equal to, well, let's write this a little bit different before we actually do that. This is 1 plus E cosine of nu to the negative 1. So that means that R dot is equal to minus P times 1 plus E cosine of nu to the negative 2 times the rate of change of what's inside. Well, the rate of change of what's inside is minus E nu dot times the sine of nu. So that implies that R dot is equal to P E sine of nu, all divided by 1 plus E cosine of nu squared times nu dot. But that can be written as P squared times E times the sine of nu, all divided by P times 1 plus E cosine of nu squared times nu dot. And then we can factor out the P squared over 1 plus E cosine of nu squared, and we get P squared over 1 plus E cosine of nu squared times E sine of nu, all divided by P times nu dot. But P squared over 1 plus E cosine of nu squared can be written as P over 1 plus E cosine of nu, the whole thing squared, times E sine of nu, all divided by P times nu dot. And this last result can then be written as R dot is equal to, well, P over 1 plus E cosine of nu is just R. So we get R squared E sine of nu, all divided by P times nu dot. So we then have R dot is equal to R squared E sine of nu, all divided by P times nu dot. So now what we can do is we can recall the following expression. So we're going to recall that R squared times nu dot is equal to H, which is equal to the magnitude of the specific angular momentum, which is equal to a constant, from which we obtain that nu dot is equal to H over R squared. And we can substitute that expression for nu dot into the expression for R dot, and we get R dot is equal to R squared E sine of nu, all divided by P times H over R squared, and the R squared cancels out, and we wind up with HE sine of nu, all divided by P. But recall that P is equal to H squared over mu, which implies that H is equal to the square root of mu times P, which implies that R dot is equal to the square root of mu times P, all divided by P times E sine of nu, which in turn is equal to the square root of mu over P times E sine of nu. So now we have an expression for R dot. So R dot is equal to the square root of mu over P times E sine of nu. So next, R times nu dot is equal to R times, well, nu dot is equal to H over R squared. So that's equal to H over R, which is equal to, well, R is equal to P over 1 plus E cosine of nu. So this is H all divided by P divided by 1 plus E cosine of nu. And that, of course, comes from the orbit equation, which gives that R nu dot is equal to, we have H times 1 plus E cosine of nu, all divided by P. But as we saw earlier, H was equal to the square root of mu times P. So this is the square root of mu times P over P times 1 plus E cosine of nu, which implies that R nu dot is equal to the square root of mu over P times 1 plus E cosine of nu. Now we can use all of that information in the expression for the inertial velocity expressed in the coordinates u. So if you recall, that expression was R dot, R nu dot, and 0, which is equal to the square root of mu over P times e sine of nu, and then the square root of mu over p times 1 plus e cosine of nu, and then 0. So we can then factor out the square root of mu over p, and we wind up with the inertial velocity expressed in coordinates fixed in u is equal to the square root of mu over p times e sine of nu, 1 plus e cosine of nu, and 0. Now that is the starting point for being able to do the remainder of the calculations. So next, we know that UR is equal to cosine of nu times px plus the sine of nu times py, and u nu is equal to minus the sine of nu times px plus the cosine of nu times py. And that, of course, just comes from the fact that if we draw the vectors, here's px, here's py, there's ur, and there's u nu. This angle is nu, and so is that angle. So we wind up with the equations that are shown above. So then, that implies that the transformation from u to p is equal to cosine of nu, sine of nu, 0, minus the sine of nu, cosine of nu, 0, 0, 0, 1. And from that, we can actually compute the position and the inertial velocity expressed in the perifocal basis. So then, the position expressed in the perifocal basis is equal to the transformation from u to p times the position expressed in u, and the inertial velocity expressed in the perifocal basis is equal to the transformation from u to p times the inertial velocity expressed in u. But we already have expressions for both of these, so we can actually go ahead and we can figure out expressions for r expressed in p and vi expressed in p. So first, r expressed in p is equal to cu to p times r expressed in u, which is equal to cosine of nu, sine of nu, 0, minus the sine of nu, cosine of nu, 0, 0, 0, 1, times r, 0, 0. So that implies that r expressed in p is equal to, well, the components become r cosine of nu, r sine of nu, and 0. And recall that r is equal to p over 1 plus e cosine of nu. So now we have an expression for the position in perifocal coordinates. So next, the inertial velocity expressed in the perifocal basis is equal to the transformation from u to p times the inertial velocity expressed in u, which is equal to cosine of nu, sine of nu, 0, minus the sine of nu, cosine of nu, 0, 0, 0, 1, times the square root of mu over p times e sine of nu and 1 plus e cosine of nu and 0. So let's multiply this out, and we get the inertial velocity expressed in p is equal to, well, the square root of mu over p comes out because it's a scalar in front. So we're left with Well, we have cosine of nu times e sine of nu. So we've got e cosine of nu sine of nu. And then we have minus the sine of nu times 1 plus e cosine of nu. That's the first component. The second component is we have e sine squared nu, and then we have plus cosine of nu times 1 plus e cosine of nu, and then the third component is just 0. So we can simplify this last result to obtain the following. So we then obtain that the inertial velocity expressed in p is equal to the square root of mu over p times minus the sine of nu, and the second term becomes e sine squared nu plus e cosine squared nu plus the cosine of nu, and then the third quantity is 0, which gives that the inertial velocity expressed in the perifocal coordinates is the square root of mu over p times minus the sine of nu, and then e sine squared nu plus e cosine squared nu just becomes e plus the cosine of nu, and then 0. Now let's look at this structure together. So we have that r expressed in p is equal to r cosine of nu, r sine of nu, and 0. And we have vi expressed in p is equal to the square root of mu over p times minus the sine of nu, and then e plus cosine of nu, and then 0. Now you can see that we know everything now in terms of the orbital elements. And the reason that we know that is because we should recall again that r is equal to p over 1 plus e cosine of nu, but p is equal to a times 1 minus e squared. So once I know the orbital elements, I know a and I know e, so therefore I know p. But because I know the orbital elements, I also know nu, so that means I know r. So that means I know everything in these last two expressions. I have all the information I need to compute the position in perifocal coordinates and the inertial velocity in perifocal coordinates. And these two quantities, together with the transformation from p to I, give me a way to be able to compute the position and velocity in the Earth-centered inertial coordinates. So then, given that we know Cp to I, we have that the position expressed in the ECI coordinates is equal to the transformation from p to I times the position expressed in the perifocal coordinates, and we have the inertial velocity in the ECI coordinates is equal to the transformation from p to I times the inertial velocity expressed in the perifocal coordinates, where Cp to I is equal to the transformation from n to I times the transformation from q to n times the transformation from p to q, and Cn to I is a function of the longitude of the ascending node, Cq to n is a function of the inclination, and Cp to q is a function of the argument of the periapses. And these matrices were derived earlier. So now we have a full set of information to be able to transform from orbital elements to position and velocity expressed in the Earth-centered inertial coordinates. So that takes us to the end of this lecture, and we can summarize as follows. Is that the focus of this lecture was on determining position and inertial velocity expressed in Earth-centered inertial coordinates given the orbital elements and the gravitational parameter. Now, in the process of doing that, we developed a method to transform from A, E, omega, I, little omega, and nu to the position expressed in the Earth-centered inertial coordinates and the inertial velocity also expressed in the Earth-centered inertial coordinates. And as a reminder, a key component of the derivation is the fact that omega, I, and little omega together form a 3-1-3 Euler angle sequence. And that's the end of this particular lecture. We're going to be using all of this information in the future when we do other material, including time on an orbit and including orbit transfer. I'm going to need all of this information in order to be able to do it. So these transformations between orbital elements and position and velocity become very important. But we'll end this lecture here.